Hey guys, good afternoon everyone. We will start the session in another few seconds, but before we do so, a quick reminder once again to all the participants, do not unmute the audio or share video or personal screens during the sessions. And I also request the audience to ask the questions, if any, at the end of the keynote address by your respected speaker. Okay. So very good afternoon to one and all. Respected Principal Dr. CPS Prakash, honorable dignitaries, industry colleagues, faculty members, participants, coordinators, and my dear students. I, Dr. Deepakar, take immense pleasure to welcome every participants and extend the warmest welcome to all of you for the 6th day of AI Conclave 2020 on behalf of Department of Management Studies, Dayanand Sagar College of Engineering. The common question that gets asked in business is why? And that's a good question, but an equally valid question is why not? I believe all of us have gathered here to answer get this answer today. So when we talk about artificial intelligence, it is considered as one of the most popular technologies being used all around the world. According to Gartner, in 2019, 37% of the organizations, which is 1/3 which were interviewed, reported that they have already implemented AI in the workflow or recognized its importance and are implementing it in the near future. The governments are also not lagging behind in the race to catch up with the speed for better governance. Thus, it's not too late to embrace this opportunity to understand artificial intelligence in business, and thus the Artificial Intelligence Conclave 2020. The AI Conclave 2020 has thus been conceptualized to address and understand the proof of concept AI projects undertaken in the industry, currently in various management domains, and to understand the ecosystem built in place for academia and industry to understand, adopt, and implement AI. I now request our beloved head of the department, Dr. K.G. Hemlata, Department of Management Studies, to welcome the gathering. Ma'am, it's on mute, ma'am.
Good morning, respected DIPANJAN, principal, my dear faculty member and students. It gives me immense pleasure to welcome Mr. DIPANJAN DEB, Vice President, Model Development, Wells Fargo, to that wonderful event, because we have been waiting to listen to him since our business analytic conclave in the year 2018. So we had a wonderful session that time. So we don't want to miss his contribution. In the sense, we are keen to listen to him about what's an update happening in the industry. So I'm so glad to bring in DIPANJAN DEB to our program. The reason is the way he comment and communicate in the LinkedIn, it's very impressive. And also this conclave, AI conclave series of interactions and hands-on sessions. So I'm so happy that, and it gives me immense pleasure to welcome DIPANJAN. And Dr. Deepak will give an intro about the DIPANJAN, and then the session will be handed over to him, so that we are here to listen to him about what's an update happening with reference to model risk. So over to you, Deepak, and then give an introduction. Thank you.
Thank you, madam. Thank you, madam. So today we'll be understanding the ecosystem of model risk assessment with our today's keynote speaker, DIPANJAN DEB, Vice President of AI Model Development at Wells Fargo. With over 19 years of experience as an analytics professional with the experience in machine learning, statistical learning, data mining, project and team development across banking, healthcare, automotive and retail domain, Mr. DIPANJAN is highly proficient in developing cutting-edge analytical solutions using open source and commercial systems to integrate multiple systems. Mr. DIPANJAN is currently Vice President of AI Model Development COE at Wells Fargo. Previous to joining Wells Fargo, he worked in various companies such as IHS, Symphony, Teleca, Genpact, Deloitte, Patni Computer System, Hewitt Associate, Creative Eye. And as a technology leader, Mr. DIPANJAN has collaborated with business teams, IT and data scientists to groom opportunities develop solutions, balance performance and explainability, test and establish effectiveness, develop ongoing performance metrics, address internal, external regulatory requirements over the years. Mr. DIPANJAN holds MBA from Annamalai University and done data mining and data analytics program from IIT Roorkee and executive general management from IIM Bangalore. Besides steering business operations, Mr. DIPANJAN also spearheads in defining the strategy and vision of the company and strongly believes in collaboration, teamwork, and leadership through involvement as the ethos defining success. So without further ado, I request Mr. DIPANJAN to address the gathering. Mr. DIPANJAN.
Thank you, Deepak. That was a great introduction. Really overwhelmed with that. Let me just share my screen. And if, can you just enable a share screen? I have a quick PPT to share. Okay, now I should be able to. Can anybody confirm that they can see my screen?
Yes.
You can see
yes,
DIPANJAN.
we can see it.
Okay, thank you. All right, so thank you, Dr. Hemlata, for giving me this opportunity to connect with all of you today. My topic for today is model risk in terms of machine learning, right? And there's a lot of research that is going on in this area recently, and I thought this is an important area. Specific on how we use machine learning, and especially in the regulated industry like banking, interpretability of models and the robustness of the models is of paramount importance, right? A little bit of change in what I'm doing right now. As Deepak was mentioning, that I lead the AI Model Development Center of Excellence, but recently, about 2 to 3 months ago, I moved to a different role within Wells Fargo, within corporate model risk. And now I can link, why am I talking about model risk, right? This is my newfound love, so to say. So within this corporate model risk team, basically all the models that are developed across the bank, even my previous group, right, the AI Model Development Center of Excellence, all models are required to be independently validated, right? And we are starting a pretty new team in Bangalore for Wells Fargo, and I'm kind of leading that area. Although this corporate model risk office is not new to Bangalore, we had a qualitative model. So basically, there are two types of models, right? So one is called quantitative model, one is called qualitative model. Qualitative models are those models which are deterministic in nature, right? So you have business rules driven, or have any Excel based formula and things like that. And there are plenty of such tools that we have in the bank, right? So those falls under the qualitative model. But where there is an element of probability is what we call the quantitative models, right? And that's what we are setting up right now. This team is new, but we are opening up quite a lot of positions. So if you are interested, and if you have anyone who is interested to join us, please keep an eye on the all the job boards and everything. So you'll be opening up quite a lot of positions to the tune of 30 to 40 positions. And I'm in this analytics space for about 15 years, but not really started in the analytics space. But my background is statistics. I was in the advertising area for about 5 years. And then I kind of started to leverage my statistics background to get into analytics long time ago. Just a quick disclaimer before I proceed. All the views, all the opinions that I am presenting today are all mine. Do not hold Wells Fargo responsible for anything. So that way I'm kind of managing the risk of the bank as well, right? So everything is my personal views. Okay, so let's move on. Before I talk about model risk, I want to give you a quick snapshot of the model development life cycle itself, right? How a model is kind of developed. Here is a high-level schematic of how a model is developed, right? It starts with engaging with business, right? Finding some opportunity. In a large bank like ours, previously we used to do a lot of POCs, right? So all the siloed lines of businesses, they already have their analytic team. They used to do some POC, try and find out, hey, can we use analytics, the new algorithms and things like that? But that's not anymore, right? So you're more serious now to embrace this technology, the machine learning, AI technology, whatever you call it. So there's a lot of regulation there. So there's a team which actually goes ahead and finds out where there are opportunities in the bank, right? And we have sponsorship from the leadership. That is very important. Unless you have a sponsorship, projects will not fly, right? So this team tries to go and find out that, hey, if we invest time and money doing this project, what's the benefit that you'll get, right? What kind of dollar either you're saving or making from this kind of project. Once that is done, the data pipelining basically starts, right? So we build up a team, and different companies have different ways of building these small teams, right? So we call it an agile team. We basically create a pool of resources from, let's say, from business, from technology, from the data science team, right? And then they become kind of an agile pod. And then they start looking at what kind of data we need to bring in to solve this problem, right? And all the cool things that you probably have learned, that all the data munging, EDA, model design, and it's an iterative process, right? And you finally find out which particular model that you want to do, right? After doing all the feature engineering and so on and so forth. Once that is ready, you test the model in limited fashion. There are plenty of techniques that probably we are aware of. Something called A/B testing. So if you have two different models, you have to test it on a small sample and find out whether this model is worth implementing, or is it giving the kind of performance that it has promised, right? You think about how do you monitor the performance of the model as you go, right? This is very important. Now, once all these things are decided, the model developer is supposed to create a documentation, right? I'm talking in terms of how it works in the banking context, right? This is very important that we document the entire life cycle, the entire journal of this whole model. Right from the business logic to what kind of variables you have used, what kind of transformations you've used, and what kind of algorithms you have used, and what monitoring plan. Sorry, is there a question? Okay, maybe not. So once the document is ready, this document is submitted to the validation team, which is present team that I'm working with right now, right? So what we do, we pick up that document and try to replicate the model, what the data scientists have built or has documented. Is it really the case, right? And in a way, kind of challenge those assumptions, right? See if the model is good enough, right? Now, the thing is, when I was part of the model development COE, I never used to like this team, because this team, the validation team, always tries to find mistakes, right? This is our job. They would always try and find out, hey, you have violated this assumption, and this is not correct, and there's a dialogue. It's not pleasant, right? But now I start to really appreciate why it is important when I think from the model risk perspective, right? There are plenty of cases where model has gone wrong, and probably you're aware of it, right? So now this model validation team, a validator would ensure that this model that has been developed is actually robust enough, right? And we held the final authority in a way to stop the model, right? If it doesn't pass all the tests that we have. So once that is passed, model goes into kind of production. So you can see it's not easy, right? So we only fancy around the modeling part of it, but there's a lot going on when you think of model development. Sorry, is there a question?
Questions will be at the end only, DEB. Please continue.
All right.
Yeah.
Okay, let's talk about what are the different models that are used in the bank, right? So the way we kind of think about it is financial models and non-financial models. There's a host of financial models like the credit forecasting, credit loss models, market risk models, liquidity, a host of different models that are called the traditional financial models, right? And also there are non-financial models which we have started to use, in terms of the customer service, the crime detection and compliance and stuffing. Now, all these models has one thing that comes free, is model risk, right? Whenever you have a model, you have a risk. Now, in a highly regulated environment like ours, the regulators have something called SR 11.7. It's a guidance so that we can manage we can govern our models better, right? So that all the problems, all the mistakes in the model can be identified by an independent model validation team, which is where I'm working right now. Once we have identified, so that we can monitor and mitigate all the risks, right? And this is by the regulation. So, so that's why, banks have started to embrace, as you know, that there are a lot of machine learning techniques that we are aware of. And in my mind, there are basically 3 different areas where we have started to use machine learning techniques, right? One is those traditional models, the traditional credit risk models or financial crime models. These are all age-old models which are pretty much done as a statistical model. We started to use whether can we use machine learning techniques to add as an alternative. See if machine learning techniques can do better than the traditional statistical model, right? There are plenty of cases of supervised and unsupervised models. We also look at machine learning models as a benchmark, right? Let's say the machine learning model is performing at a certain level, and can the statistical model work in that same kind of performance, then we don't use any machine learning model, right? So we know that, hey, this is the max that we can get. Also, there are techniques to find out because machine learning models captures a lot of non-linearity, right? And there are interactions that we can find out when we run the machine learning type of models, and we get a lot of understanding and use all this understanding and better the traditional statistical models. So this is one area where we started to use a lot of machine learning models. Also, machine learning models are used where traditionally there are no models as such, right? For example, compliance area, right? Conduct risk or customer assistance. You're seeing a lot of adoption of chatbots, which uses a lot of NLP, natural language processing techniques, even to monitor our own behavior in the bank, right? These are all conduct monitoring. How do we understand our customer complaints better? So these are some of the emerging area where machine learnings are widely used these days, right? We started to embrace the machine learning technique. Another area is the derivative pricing and market risk area, and this is where we use a lot of partial differential equations and stochastic processes to price our derivatives, right? Where we can invest our money, right? And these are all heavily numerically computationally intensive algorithms that we use. And we started to see can we replace the complicated Monte Carlo simulations. People who are aware of this area, they use a lot of Monte Carlo simulations, right? And we are starting to see if we can use the GANs, the generative adversarial network type of algorithms to create or simulate the process and potentially replace those Monte Carlo simulations. So these are some of the areas that we started to use. Like I said, right, the famous quote from George Box: all models are wrong, right? And some are useful, as he says. But the problem is, when the model fails in a banking context, it causes a lot of harm for us, right? And some unintended consequences. Give you an example. Let's say people who are familiar, well, most of are in Bangalore. You are probably familiar with Quick Rides, the service provider, right? That the cab sharing app. I used to use Quick Rides quite a lot, and if you have seen, they have tried to advertise pre-COVID era, a lot of advertisement to onboard, both customers and the cars, right, the car owners. Obviously, they had a model, right, forecast their revenue stream, and they probably got a lot of funding showing their model, right, the forecasting model that, hey, we'll be making a lot of money. So a lot of investors might have invested there. But what happened after COVID, right? They're not in the road anymore because nobody's taking out their card. They probably never thought about COVID at all, right? There are plenty of such companies. They had a forecasting model for sure, which are not working. A bank like ours, we cannot afford to have such a model, right? Quick Ride can say that, hey, few investors lose their money, but if a model like this fails in the bank, it is going to cause a lot of problem. The US economy can go down, right? And if US economy goes down, the shock will be felt around the world, right? You cannot afford to have a faulty model. So there are plenty of use cases here. I have quoted some examples here. If you have a model, you are basically hedging. If you have mishedged, you have a lot of market risk, right? What's a good example? Staffing, right? Understaff. If your branch is understaffed, and if you have a long wait time, you'll have a reputational risk, for the bank. Fair lending is a big deal, right? If you are approving credit for non-credit worthy, and if you are focusing on certain strata of the society, then you have a compliance risk, and that can get into some kind of legal risk, right? So these are some of the areas where we need to think about as a validator, as a model builder in the bank. How do we do this validation, right? When any model that after it has been developed by the data scientist, it comes to us, and there are a few things that we check, right? First off is we try to find out the matrices, right? So when can I say that a model is failing? So we have to define those matrices. First of all, right? And then not only define those matrices and then say that, hey, this is my tolerance level of the model, right? If it goes below this or above this, then we say that it has failed. Now, once you have defined that, we try to look at the root cause, when those matrices can be bridged, right? It can start from anywhere. The model development starts from data itself, right? And what kind of variable you select. Different models have different assumptions, right? And how you have implemented and using the model, right? You have to check all that. Not only we stop there, then we check, can we test when the model can fail, right? We perturb the data, right? It's like software testing, right? When you build a software, there's a testing team, right? So it tries to find out when and where the model failed, right? So there's a lot of work that happens here to identify where the model can fail, right? Once we have done that, we try to analyze the impact. If the model fails, then what would be the consequence of the model? And basis that, we create our mitigation plan, and monitoring and control and all those things comes into the picture. This is like a very high level how a model validation takes place, right? This is how we do model validation. Just to give you an example here, this is not a banking example though. Here you see an adversarial attack, how a model can fail, right? The image that you see here, it's an original image of a cancer, and the model says that it's not a cancer, it's a benign. But then if you perturb this with a noise, it's called an adversarial noise, and the model changes its behavior. But if you see, it hasn't really changed visibly anything, right? And then here's another example. This has been quoted from this paper. So if you're interested, you can take a look, right? And you just tilt the image and it becomes malignant from benign, right? Then you change a little bit of text in the description. From high risk, it becomes low risk, right? And then you have the tagging, right? The coding itself. If you just change the order a little bit, it becomes from denied reimbursement to approved reimbursement. So these are the areas that the model at the outset it looks nice, but when you just poke it a little bit, perturb it a little bit, things changes drastically, right? And these are exactly where the model validation team comes into the picture. It's not just building the model, test it in all the adversarial areas and see where the model can fail, right? Here's another example. You see the sentiment analysis here, right? You see there's a text here. It says it's a positive sentiment. You just change one word here to this, and the sentiment changes drastically, right? You replace a word from film to footage, and the entire deal changes, right? So these are the areas tells us that, hey, we have built this model. It looks good from the surface, but when you change it a little bit, just a little bit, which doesn't even appear on the eye. For example, here, things changes drastically, right? What are the common causes of such model risk, right? Like I was saying, right, it starts from the input data itself. You have to be aware that the data that we use are not biased, right? So how do we check that? Second important thing, which is often overlooked, is conceptual soundness, right? And I'll talk a little bit about what is this conceptual soundness is all about. And the third thing is model robustness that I just touched upon a little bit, right? The other thing, which is again overlooked quite a lot, is people are obsessed with model performance. Data scientist wants to build the model with 4 digits precision of accuracy, right? But the real world changes, right? So you build a model with, you're aware of this train test split, right? But there's a point in time data. As you transverse to time, your data basically changes, right? COVID is a good example. A lot of variables have drifted away. So the model will not hold its truth, when such kind of data changes. Model change control, right? When you produce a new model, you basically change the whole coefficient altogether, right? I'll probably give you an example. And also, when you, how do you manage all those change control is again common causes, right? Here's an example of what I was talking about, this conceptual soundness. So what we say here is, does the model even make sense, right? From the looks of it. Can we even trust the model, right? And when it is going to fail? So these are some of the questions that a validator always asks. Now look at this picture here, right? This is a credit model. And then these are different variables here, right? And how the variable changes. So the FICO score is like a credit score. Conventional wisdom would say that if the FICO score is high, person is credit worthy, whereas the loan to value, if it is low, then the very less chance the person will default, right, on the credit. But when you change the model, right, your accuracy remains the same, but the direction of this whole thing changes, right? And the FICO really goes down, CLTV goes up, but the model performance remains the same, right? Now, does it make any sense, right? You can check your model accuracy, performance, it's all fine. at one region it works fine, on the other region it doesn't work fine, right? So these are the cases where we say that we cannot trust this model. It is rubbish, right? Here is another example of, let's say, this is it's a toy example. So let's say you have built your model with this input data, right? So your model would only operate well within this range, right? But as the data drifts away, like here, you cannot trust the model. Model will start behaving really, really bad, right? Now it is important for from the interpretability and explainability perspective, because all the customers that we have, and if we deny their loans, right, and they have the right to ask us, why did you deny my loan, right? And we have to provide reason code, right? So if you build a very, very complicated model, you don't know what's going behind the scene, right? So it's a black box model that you're aware of. We don't know what's going behind the scene. So it's a regulatory requirement that we have to say, hey, this is the reason why the models are failing, right? Yeah, so this is an example that if you have a linear model, right, you know that this is the minima, right? But what happens is when you have a machine learning model, there are plenty of local minima that we have, and all the models will give you good performance, right? When you basically retrain your model, you basically jump from here to there, and you don't know, and you're trying to defend one model. So this is the issue with the machine learning model. But so I guess everybody understands why this interpretability and this robustness is required. There are a few techniques I'll talk about, touch upon a little bit, and this is an active research area. Nobody has a sure shot answer to this, but I want to talk about this and give you a sense of what happens and why it is so important, right? Okay, so now we talk about interpretability. What is this interpretability all about, right? So let's say we have a linear model, right? And linear models are considered highly interpretable because you can easily find out what these variables mean, right? You can say that for an example like a linear model, you can make a statement like this, right? 1 unit increase of x2, the y increases by 6 units. So you can easily say that this is what it is, and you know the weight, you know the direction and the magnitude both, right? Also, in models like decision tree, right, it is also highly interpretable. Although there are no effects like this, but these are again rules. And this is a toy example from the famous techniques arrival dataset. It says that, hey, if the person was traveling in first class, all of them kind of survived. Second class, male didn't survive. Third class, nobody survived, right? So you can still understand if you look at the tree from the top, right? So these are considered as highly interpretable. Any layman can understand this, right? But as you go to some of the complicated ensemble techniques, things start to move very differently, right? So here's an example of a random forest. There are a lot going on, goes behind random forest, but this is just an abstraction. Basically, in random forest, you create separate trees, and then like a small tree, and then you find out the prediction from these different trees, and then you kind of vote for it, right? It becomes a little complicated to explain, right? So there are techniques that are available in random forest, which gives you something called a feature importance. That's like a global explanation is what we call, but it gives you kind of a magnitude, not like a direction, right? Then when you get into the gradient boosted trees type of models, it becomes a little more complicated. It's like you build a smaller tree and then the misclassifications are weighted high, and you iterate through this, and then you kind of find the right model, right? And this is an example of an extreme, the XG boost, the extreme gradient boosted machine, right? Things are quite similar, but it uses a different regularization converge further, right? So now this kind of model becomes a little difficult than the traditional, the linear regression type and decision type models, right? The third category of model is what we call a black box model, right? Which is the neural network type model. So you know that there are plenty of hidden layers out here, and we have to understand, hey, what is the effect of X1? Well, you can calculate it backward, but then the equation will be so complicated, nobody will be able to figure out, right? So a lot of interactions going on. It becomes very, very difficult to interpret this model, right? The dilemma here is your simpler models are kind of highly interpretable, but they are not very accurate, right? Whereas the complex models are accurate, but they are not interpretable. So what do you do? That's the problem that all the data scientists, feel. Especially when it comes to, hey, we'll apply machine learning, but what's the deal, right? So I said, okay, our performance will increase, but then we don't understand it. Why? The inner working, interpretability, right? So one way of dealing with this is kind of look at the simpler model and see if we can increase their accuracy in some way. That's where the machine learning technique comes into play. I talked about in the beginning, right? From the machine learning techniques, you can find out the interactions, various transformations and things like that, and variable selections. You apply different polynomials and things like that, make it accurate. But then it becomes very, very difficult, right? But you can go that far. The other way of looking at things is, how about looking at the complex models which are highly accurate and try and see if we can interpret them better, right? That's the whole deal that we are working towards, and a lot of researchers are working towards. Okay, plenty of solution out there. I'll probably mention a few of them. One of them is called fancy name to it. It's called ELI5, and what it does is, you can input, you create a model object, right, and then pass it onto ELI5, gives a clean API, and it gives you something like this, right? And you can clearly see which variable is contributing to the decision, right? The good part is it not only provides you a global view, like how the model itself, the whole totality of the model is doing, but you can also find out at a local level, at an observation level, like here is an example, right? So it's a particular observation and why it has, coded something, and you can know, you would know why it has happened, right? So it provides both what we call global and local interpretation. Okay. Second one is called LIME, right? So local interpretable model agnostic explanations. This is an interesting paper, and link is incorrect, so I'll probably change it. This is from that paper. There's this visualization that they proposed, that this is a model which is highly non-linear here, right? What they're trying to do here is to separate this pink from the blue, right? So pink region from the blue region, like about two different classes. So what they do is they pick up you pick up one area of a particular local variable, and you're trying to explain this, why the model has predicted this to be in the red region. What it does is you select that observation and then try to sample around this region, right? And try to fit a linear model here in this locality. This is a linear model, right? And then you get, the linear regression type coefficients that, hey, this is the reason why, like a logistic regression. But if you have to segregate here and find out why a particular data point here is red and not blue, your linear regression will be something like this, right? Like a straight line, something like this, right? So your explanation will change depending on where you are in that locality, and that's why it is called a local interpretable model agnostic explanation. So you cannot have a global explanation with this, but at least a local explanation can be arrived from, and it can take into consideration any kind of modeling. I think these days they also take the neural network type models as well in the API. So you can input any kind of complicated model and create this local explanation in some way. Okay. Third approach is called SHAP, Shapley additive explanation. This has been derived from the famous game theory. Basically what it does is, it goes and iterates the model and takes out one variable at a time, and it has to see the effect of that variable, right? And you train a model and with and without the particular variable and see how it fares. And in the end, it gives you something like this, right? This is very interesting. It says that these are the variables which is pushing the prediction to this side, and these are the ones which is trying to push the prediction on the other side. You can see that effect very, very visually from this explanation. This is a local explanation at an individual data level. It also gives you a global explanation like this, and it's like a feature importance kind of visualization, right? That you get for any kind of complicated XGBoost or any other ensemble techniques, you get at a feature level, what the explanations are. So it means that for feature 5, as an example, higher the value of feature 5, it is tilting towards the positive side of the prediction than the negative side. So it's very intuitive in a way, right? But all said and done, these are all called what we call post hoc analysis, right? So we are trying to fit a model on the prediction of the model, right? So you cannot be highly accurate about it, right? For example, on the line, when you're building, let's say this linear model, if that model is not good enough, right? And how would you know if those statistics are not good enough, then this model explanation is not good, right? So these are some of the limitations. Yeah, I mean, this is something that I had, but I'll probably show you something more as I kind of wrap up. At Wells Fargo, we are doing an active research on something called explainable neural networks. Okay, you can look it up. It's a little, it's available in archive, and this is all Wells Fargo team, and we have published this paper. What we are proposing here is neural networks, as we know, they're black box in nature, like in this diagram. Where is the diagram? Here. We are trying to propose some idea that, hey, this neural network, if we do it differently, it can become highly explainable model. You can get beta, you can get linear regression type of coefficients from from this layer, right? Like an additive effect. So if you're interested, take a look at this paper, download, read about it. And yeah, we can connect more on this. That's it from me today. Anybody has any question?
Thank you, Dipanjan. Now we are open to questions from the audience. So first and foremost, request you to tell your name first and then ask the question. And please mute the audio after you have asked the question. Thank you. Have any questions?
Sir, hello. This is Chetan from third semester MBA.
Mm-hmm.
I have a doubt. Like while validating the model, should we behave like a data scientist or a business analyst? So to simplify the statement, should we consider the statistics into consideration, or the business scenarios into the consideration?
You have to challenge the data scientist, right? So that means you have to operate at one level high, in a way, right? So whatever the data scientists have done, first of all, what we do is we kind of replicate the model first, and then we build a challenger model to say that, hey, we have built a better model, or a simpler model which gives similar kind of performance. So you have to think from all direction, not just statistics, not just data science, business, everything. And the starting point is the document that I talked about, right? What in Wells Fargo we call it model development document. This is where we start. We have to challenge, find out problems wherever we get. We discovered there's a problem.
Thank you, sir.
Sure. Good question.
Yeah. Any more questions? Dipanjan, before they go ahead, one question is, when we talk about complexity, when we talk about complex models and then we want to interpret, as you were referring to.
Mm-hmm.
So specifically when it comes to these deep neural networks which are there,
Mm-hmm.
deep neural networks, when it comes to interpret, or in terms of the interpretations, have you got any cases where you can explain a simple example on considering deep neural networks, which are difficult to interpret in the beginning, but becomes very, very easier when you have to look at a simple case on just a classification based method also? Will it be possible?
That's the reason I'm proposing this, and that's an active research, right? The XNN. So that's the name itself is called Explainable Neural Network. Right? So when you build like a large, very deep, with a lot of hidden layers, you cannot explain those, right? Because you can actually, if you look back and then you'll find out the equation anyway, but it becomes very difficult for any layman to understand what's going on, right? So that's why we are proposing this idea of explainable neural network. If you're interested, go and read this paper. And we are trying to actually create a library. We'll make it open source, hopefully at some point in time. Our team is constantly putting a lot of effort, time and money, both in this. And we feel that it's going to be a game changer if it happens.
So any more questions, guys? Now, another question that I would like to ask is, now most of the analysis also that everyone is doing has got a lot of independent variables to start with, right? So if you have got a lot of independent variables, so there comes a point wherein you have to judge that keeping few independent variables aside, because they are really important, and then the decision has to be taken on which all other independent variables to include. So if this is the case, what kind of decisions are you taking on a day-to-day basis when you go for these model risk evaluations?
So honestly, that's the job of the developer, right? We have this business problem, and then to solve this business problem, we will be using, let's say, we'll start off with, say, 500 independent variables to start with, right? And then you kind of iterate through your model and find out the techniques, variable, elimination, lot of deals, right? Lot of techniques out there. So you iterate and find out which set of variable is giving you the performance that you're after, right? And if you're not happy with the performance, then you go back to the table, right? Talk to the business and find out more about it. That, hey, we have exhausted all the different transformations that possibly I could. We are not able to achieve the kind of performance that we are after, right? Maybe something is missing. Start a dialogue with them, and that's the iteration that goes on and on, right? It doesn't even stop from on the after you have selected the model, right? You monitor the model as it goes, and you'll see, and this is quite well known that model deteriorates, right? It is a good example, right? Or many models, not only in the banking sector, right, across the board, right, have failed because some of the assumptions were incorrect. So they are now retraining the model, refitting the model, and a new set of variables with their weight will come about, right? So it's a continuous process.
Thank you, DIPANJAN. So, any questions?
That's a good question. Yes.
Sir, I have another question here.
Mm-hmm.
So keeping coding and validation into consideration, we have so many pre-built models, that is software, say, for example, JMP and even Microsoft Azure, which provides pre-built models to evaluate the data. So is that good, or conventionally writing the coding in Python and validating, is that good? Which one is better, sir?
Well, there are certain areas, the pre-built models, and it's an interesting area as well, right? So something called transfer learning, right? Especially in the image detection area, you have pre-built models. You basically start from there. You have this whole neural network. You open the neural network, chunk off few final layers, and you kind of retrain it, right? So you don't have to go through all that loop. Chatbot is a good example that to build a chatbot from ground up in a company is very, very time consuming, right? You can do it, but is it worth? So business takes those decisions whether to buy a pre-trained model and then use it and then train it, right? Train it to your need and then make it available. So there are plenty of techniques available, but there are cases where it is very, very. I cannot really quote you an example because this will get into some kind of IP side. We have solved certain problems, and those are the areas where we build models from ground up because those models doesn't exist in the market, right? So when you have a very, very business focused business problem, which is unique to you, right? You probably would not be using a pre-trained model at all, right? Pre-trained models are all